So, hello everyone, I'm Rishabh Ayush and I'll be taking the lecture talk on Pythagorean Theorem and its applications. So, this talk will include everything about Pythagorean Theorem related to geometry and number theory. And we'll also see some of its applications in real life and also the infinite descent, which is very useful in various Olympiads. And the screen is not moving. Okay, so what is Pythagorean theorem? It's one of the most famous results in mathematics, like one of the most ancient ones, which is that if you have a right angle triangle with side lengths A, B, and C, where C is the hypotenuse, so you have this relation. So I guess everyone knows this theorem, and we'll modify this definition later in the later slides, and you'll be amazed to see that. Okay, so this is one of the proofs of Pythagorean theorem, like one of the pictorial proofs which you could do by area relations. So I'll just give a brief talk about this. So you can take this side as A and this as B, like this side length, and you take this side as C, and this is a square actually. So what you can do is you can get C square equals to A square equals C square equals to A square plus B square. Is everyone aware about this proof? You can type it in the chats.
Yes.
Okay, yeah, feel free to unmute and speak because discussion is very good way of interaction. Let's see the next slide. Um, I can't move to the next page. Okay.
You can try resharing your screen.
No. Okay, it's fine now. Um, so there's some error in it. Wait, let me fix that first. So, does it show the screen properly now?
Yeah.
We can do this way. So, this is another proof which you could do to prove the Pythagorean theorem. It says using the theory of induction. So I won't be going over this proof. It would take a lot of time to do it. So I just included this because it's really fun to do it using this way.
It was
So
included in the video that you shared, right?
yeah, you could see that video and get some ideas on how to prove using induction. So I'll give a brief hint on it. So you see this triangle, you'll be using this thing to prove the Pythagorean theorem. So you take the side lengths, this as A, this as B, and this as C. So what does this statement says? That you could always find, so this triangle would be translated to this, and the whole thing gets fit into this. So the area of this thing and the area of this, the below square and the four congruent paths would be equal to this thing. So think about doing this problem using induction, and you could discuss with your friends and anyone you want. We won't be going over this talk. So let's see some examples of Pythagorean theorem. So it is analogous to saying that we have this equation and we find the integral solutions to it. So you have this a square plus b square equals c square, and you try to find the values of a, b, and c. So can you give me some examples of the solution, like the examples of Pythagorean triplets?
3,
Like
4, and 5.
3, 4, 5.
3K, 4K, 5K.
I think this is one of the most famous examples in the literal world. So any more examples? You could type it in
12,
the
5,
chat.
and 13.
Yeah, that's one of them. 5, 12, and 13. See, I wrote those. when
9,
you-
40, 41.
Yeah, that is one of them. 9, 41, 43. And wait, actually,
9, 40, 41.
yeah, 9, 40, 41. Yeah, right. And these are some more: 8, 15, 17, 7, 24, 25. So you could also name some other examples. Any guesses? Or you could type it in the chats. Feel free to unmute and speak. Anything works.
15, 20, and 25.
Yeah, yeah, we'll see more about it. Whenever we have such a triplet that's A, B, and C related as A square plus B square equals to C square, we call it a Pythagorean triplet. So everyone knows this, and there's nothing special about it, but just include it so that you have the knowledge about it. Okay, so what is a primitive Pythagorean triple? Primitive is nothing but relating it as GCD equals to 1. So whenever we have the GCD of A, B, and C, where A, B, C are the variables in equations A square plus B square equals C square. So we can say that GCD of A, B, C equals to 1, or also we can say GCD of A, B equals to 1. They both are equivalent relations. Do you see why they are equivalent?
Yes.
Okay, so I can, okay, there's a question. Okay, no.
No, I don't.
Okay, so basically, this GCD of ABC, it includes three variables where you have their GCD as 1. So it is equivalent of saying that GCD of two of them would be equals to 1. And when two of them are equal to 1, so you could say that if we have three of them, they will be also equal to 1. Does that make sense? Feel free to unmute and speak.
I'm
Okay.
still thinking.
Can you please explain it again?
I said that if we have, let's see from the back, like if the GCD of AB is 1, so how can we say that GCD of ABC would also be 1? So GCD of AB equals to 1 means that AB are co-prime. And if that's co-prime, they don't have a common factor within them. So the three of them, it includes AB, and they don't have a common factor within them. So we can say that they have a GCD of 1. Does that make sense now?
Yes.
Okay, cool. So there exist many Pythagorean triples, which are actually a version of the primitive Pythagorean triple. Actually, the scaled version of primitive Pythagorean triple. You have 3, 4, 5, and when you multiply 2 to all of them, you get 6, 8, 10. So you see, there are infinite Pythagorean triples, which are actually the scaled version of the primitive ones. So any questions as of now?
No, it's clear.
Okay, fine. Let's move to the next slide. So the question is, can we find all the primitive solutions of the Pythagorean theorem? So does anyone see why we can find? Or anyone has some knowledge about it? If not, that's fine.
M square minus 1, 2m, m square plus 1.
Can you repeat it again?
Yeah, m square minus 1, 2m, m square plus 1.
Yeah, that's actually when you have n equals to 1. But actually, you can try to find all the Pythagorean triples. We'll see it in future slides. So yes, we can actually find all the primitive solutions, but not necessarily to other equations. By other equations, I mean that are not of the form a square plus b square equals c square. So we can find it here, and the answer is the parametrization of the equation. So we'll see how parametrization works and how do we apply, and we'll solve some of the problems using it. So a lot of work in number theory and algebraic geometry explains this parametrization of the primitive Pythagorean triples. So we'll see how does that work. will not be going over algebraic geometry. It's actually the using the affine spaces and vector spaces, which will be very high according to this talk, like the level of this talk. So we'll not be going over that. We'll be using the version of the number theory, and we'll be able to understand everything. So Hilbert's 10th problem, like one of the most famous problems in ring theory and algebraic geometry. This RTAG means ring theory and algebraic geometry. Like it asks if there exists an algorithm to determine whether a polynomial has a solution in integers in several degrees. So you could read about Hilbert's 10th problem, like it's solved now, which was one of the most famous open problems back then. So it has some applications of Pythagorean theorem. So now let's see how parametrization works. So you have this equation a square plus b square equals to c square. Anyone see how parametrization works, or what parametrization is? Any questions on that?
Can you please explain that or this?
Okay, I'll explain what parametrization is. It is a kind of thing where you use other variables to express another variables. Does that make sense?
Basically substitution, right?
Yeah, basically substitution. You use clever substitutions to find the values. So we can divide by c square to get this thing, that is a by c square plus b by c square equals to 1. So we'll see why I divided it. And this is something which we already know. Oh, okay. So does this seem familiar to you? Like this equation?
Yeah, x square by x square plus y square by b square equal to 1.
I mean, does it make like, how do you familiarize with this equation? Is it of like, think of it in some geometrical way? You can type it in the chats or ask.
In more general sense, it's the equation of ellipse.
Ellipse is x square by a square plus b square by y square equals to 1. But here the variable in the denominator is c square. So actually it's
Circle.
I
the
think it's
equation of
related to circle.
Yeah, it's the equation of circle, and also circle is a special case of ellipse. So this is something which you already know. We talked about it. It's the equation of circle. And now what we can do is extend our search for rational solutions of this equation, and not just work with the integer solutions for the equation a square plus b square equals to c square. Does that make sense?
Can you repeat, please?
Yeah, I mean to say that we'll be searching for the rational solutions to this equation, that is a square plus b square equals to c square, and not just integral solutions, because we want to find every solution in this literal world. Does that make sense?
Yes,
Yeah,
yes.
it's clear.
Okay, fine.
So like when you find a rational solution, you can multiply by LCM to get an integer solution. That's what it means, right?
Yeah, actually you can divide or integer by rational number to get the solution. It is also like saying equivalent of multiplying or dividing.
Yeah, fine.
Okay, let's see the next slide. So what do I mean by rational points on circle? It is a technique used to find the rational solutions, like all the rational solutions. We'll see how we find. So consider the 2 points -1, 0 and x prime, y prime on the circle, and make a line through both these points. So why I choose -1, 0 is a special case. Like you see, I'll talk about it in the later slides. So the slope would come out to be rational as we have rational points. And this -1, 0, I used it because when you find the slope with the points x prime, y prime, you get y prime minus of -1 by x prime -0. So does that make sense?
Yes, yes.
Okay, so Does anyone have any doubt why I choose the point -1, 0 and not any other point?
Even if you choose 1, 0, it is still simpler, no?
Yeah, it's simpler. You can try to prove in that way also, and it would give the same value, but the solutions to x square plus y square equals to z square, the value of x and y would get reversed, like they get swapped. Does that make sense?
Yeah.
Yeah, I mean to say that the value you get from x prime y prime here, you'll get the value of y prime comma x prime from 1, 0. You can try actually proving that.
Oh, wait, from 1, 0, y prime, x prime wouldn't come from 0, -1.
Yeah, it won't come from 0, 1. I said 1, 0.
No, I mean 0, -1. Because in that case, you swap. No?
Yeah, you can actually try to prove that.
Okay.
Okay, but it's just a clever technique to find the rational solutions and nothing else. So now let's see the proof of the parameterized equation. So you have the slope of the line. Actually, I included a figure. Let me see. Just a moment. Okay, okay. I can explain this with a diagram. So let me annotate. Um, yeah, so this is a circle and the point -1, 0 would be here. So let me choose the color and there we go. So -1, 0 would be here. And let's suppose that x prime comma y prime is here. So you can find the slope of this line. So it will come out to be y equals to t times x plus 1. Does that make sense? This is -1, 0. If you have any questions, you can ask. Just private message me or unmute and speak. Okay, I'll take that as a no.
What's T?
T is the slope of the line, like t
Oh.
equals to,
Yes, yes. It's a
okay. So let's move to the next slide. And so now we have two simultaneous equations, that is x squared plus y squared equals to 1, and the equation that we found from the slope of the line. So does anyone see how we can use parametrization to find the value of one in terms of the other?
you can substitute y for t times x plus 1.
Yeah.
Yeah, we'll use that only. So now we could just substitute second one into the first equation and solve. So we substitute the value of y in terms of t and x to find the value of x in terms of t.
I want to confirm that t equal to y dash upon x dash plus 1, right?
So we took the prime x prime y prime as a general point, but we solve it in terms of x and y. So it is y equals to t times x plus 1. Does that make sense?
Sorry, what did you say?
I said that we took the point. Okay, let me move to the previous slide. And so x prime comma y prime is a general point on the circle, and we solve it in terms of x and y, which are our concerned points here. So I used x prime comma y prime just for a general point and to give a definition of slope. And I used this thing to prove, like to find the value of x in terms of another variable. Does that make
Okay,
sense?
I got it.
Okay, sure. Okay, fine. Okay, so now we can just substitute the second one into the first equation and solve. So we get this equation after the substitution, that's x squared plus t squared times x squared, x plus 1 whole square equals to 1. So we can apply the discriminant formula to find the value of x. So we can do the manipulations and check this to find the value of x in terms of t. So I'll give you 1 minute to find the value of x in terms of t from this equation. So actually try this out. So you have 1 minute for it. So anyone working on it?
Yeah.
Okay. When you have done, you can unmute and speak or type it in the chat. Yeah, using quadratic, we find the value. Mhm. So what you can do is club the terms of x square with together and the terms t, like there won't be any t, so you can find, you can use,
Minus. Oh, sorry, I missed.
take your time, you have 1 minute. If not, we'll see then.
I think it's minus 2t square plus or minus the root of 3t to the power 4 plus 1 divided by 2t square plus 2.
Not actually, it was close, but not really. Okay, we'll see the next slide. You'll get the idea. So we'll get x equals to -1 and another as 1 minus t square by 1 plus t square. So you can see how we do it. So here we have x square plus t square. So I'll just give you an idea quickly. So let me write it. You have 1
Yeah, I
plus,
got it.
you have this equation. I'll just write the equation and you can do the manipulations later. This is 1 plus t square times x square. Okay, this is x square plus t 2 times t square x plus of t square minus 1 equals to 0. And you'll see that we are not interested in this solution. Can anyone think about it? Why aren't we interested in that?
I think
It's
it
a
has
fixed
something
solution.
to do-
We want general solution.
But it can be general solution for every equation.
That's
It
because
might have something to do
that's
with the
because the
original
first-
definition.
Yeah, only one of you speak and okay, one of you can speak now. Yeah, unmute and speak.
yeah, okay. That's because the first trivial intersection between the circle and the line was -1,0.
Yeah, that's actually a good point. Yeah, that's actually right. So the point -1, 0 was our first equation. So the intersection was here with the point -1, x, y, -1, 0 and x, y. So this was one of the first trivial solutions, like first trivial intersection. So that's actually a nice observation. Okay, so you could find the value of x with this equation. Will you be able to do that?
Yeah.
Yep.
Okay. Let's move to the next slide and see. So why are we getting one of the solutions is x -1? So we discussed about it. So, okay, let's move to the next point. Well, we are interested in finding the second intersection, that is x equals to 1 minus t square upon 1 plus t square. And we can put the value of y equals to t times x plus 1. So we put the value of x from here and we put it here. So we can find the value of y. So we get y equals to 2t upon 1 plus t square. This is just manipulation. You could do it. Like you find 1 minus t square upon 1 plus t square and plus of 1 plus of 1 plus 1, and then send the denominator to the numerator. That is, it would t square terms get cancelled and you have 2t upon 1 plus t square. Does that make sense?
Yeah.
Okay. Let's move to the next slide. And so how are all the points rational? So as t is rational, we take t as m by n form, or you could take p by q form. I just took m by n. So then we have the points n square minus m square upon n square plus m square, 2m n by m square plus n square. So you could find it from here. Just substitute the value of t as m by n and do the manipulations. Does everyone see why that works?
Yes.
Yeah.
I'll just do it quickly here. So we have 1 minus t square upon 1 plus t square and 2t upon 1 plus t square. So you just substitute m by n here, 1 plus t square, and then do the manipulations and find this value. So I'm leaving it as an exercise to you. So there's a question. Okay, no. Let's move to the next slide. So we have, okay, so now we can substitute this value, which was our original equation of x square plus y square equals to 1, which we found from a square plus b square equals to c square, and then we divided c square. So does that make sense? I'll
Yes.
explain this thing. So you see, you substitute the value of x and y here. So you have n square by n square minus m square upon n square plus m square, and then you square plus 2mn upon m square plus n square, and then you send the denominator to the numerator on the other side. Okay, let's move to the next slide. This should make sense. So familiar equation. So our question is there an equation similar to the previous equation, that is this one? Anyone? Well, we just saw it a few minutes before.
Can you please repeat the question? My net lag.
Okay, so our question is that do we have an equation similar to the previous equation, that is this one? Do we have an equation similar to this or no?
Yeah, that 1 minus t square one.
Actually has a square missing. So sorry about that. So do we have an equation similar to it?
X square plus 5 square equal, a square plus b square equal to c square 1.
Yeah, exactly. That's the equation. It's the equation of Pythagorean theorem. The equation used to find the Pythagorean triples. And so let me clear those. Okay, so this equation is very similar to this equation, that is a square plus b square equals to c square. So you can substitute the value of a as n square minus m square, b as 2mn, c as n square plus m square. And let's see one example. So to make things more clear. So this is the example of rational points on a circle. That's minus 5 by 13, comma 12 by 13, minus 1, comma 0. So you can actually try to find the slope. I'll give you 1 minute to find the slope. I have given the slope as 3 by 2, but I want to confirm from you all. Okay, so one of the person has done it. So anyone else who has done this?
Yep.
Okay, so
Yes,
is the slope coming out to be 3/2 or something different? Okay,
yeah, 3 by
so
2.
It's correct.
okay, so that means this is correct. Okay, let's move to the next slide. So the proof for primitive Pythagorean triple. So I'll actually try to prove this. So is the primitive Pythagorean triple that we got, is it really primitive? So what we actually find to do, what we actually want to try is that we want to know if the GCD of the two numbers is 1. Which two numbers? Does anyone have any idea?
A and B.
Minus 5 by 13 and
A
12
and
by
B.
I'm not talking about the example, but like in general, that is, we are trying to
Like
find,
the
A
M
and
and
B.
N equation.
yeah, from the equation a square plus b square equals to c square, we are actually interested in finding the GCD of a and b. So we need to find if they are really primitive.
we have value of A and B as in terms of N and M. So we use that now.
And
Yeah.
the GCD of M and N is 1 because we defined T to be rational. So M and N have to be co-prime.
Yeah, right. So let's just assume for the sake of contradiction that P is any prime that divides n square minus m square and n square plus m square. So then we can write this thing, that is n square minus m square equals to pk and n square plus m square equals to pl, because p divides n square minus m square. So you learned this in modular arithmetic lecture, so there's nothing new about it. But does anyone have any doubt till now?
I had doubt like why did you use that minus 1 comma 0 point?
We actually discussed that it's actually a clever technique to make the slope easier to calculate. Like you
So
have
just
minus,
that only, na?
yeah, it's for that only. It's just a clever technique that you find the slope and you have less variables and nothing more.
Why not 0 comma 0?
0, 0 wouldn't lie on the circle. It would be the center of the circle. So you want to find the slope of two lines that are actually on the circle. Does that make sense?
Yeah, yeah.
Okay, so we shall proceed to the next slide. So then we get 2n square. Then we add both these equations and we have this thing. So it's just manipulation and nothing clever. So we'll use this in the next slides. So we see that p divides both 2n square and 2n square. So you see why?
Yeah.
P will
So
actually
we
divide
get the
2n square.
contradiction.
Can you repeat that again?
So do we get the contradiction because N and M are supposed to be co-prime?
The voice is not actually clear.
He's saying so we get the contradiction.
Not really now, but we'll have to provide more details to it. Let's see next. So P divides both 2m square and 2n square, but the only prime that divides two terms is 2, because P is a prime and the prime that divides 2 is 2. Does that make sense?
Yes.
Okay, so we can say that P will divide both n square minus m square and n square plus m square if and only if both are even and odd from this thing, because it divides 2. So they both need to be either even or both needs to be odd.
Why P can't divide m square and n square?
It doesn't divide them individually. Let me see. So it divides their difference and their sum, like the square. So it does not imply that if it's divide the square, it will actually divide its square root. Like if p divides n square, it does not signify that p will also divide n. Does that make sense?
Okay.
I mean to say that oppositely, like the negation of that. Okay, so we see the next slide. So we already know that m and n are relatively prime from the t equals to m by n, as they were rational numbers. So both of them cannot be even at the same time. Does that make sense? If they are even, they would cancel out and it would
Yeah,
again
yeah.
be co-prime. Okay, so that makes sense. So in both the, okay, there's a, okay, actually, yeah, I missed one thing. If p divides n square, then p divides n. Sorry about that. Let me check that. Because, okay, let me clear that here. Sorry about that. If p divides n square, as it will have one factor in that in this, and this will have two factors of that number if it divides. So p will actually divide n. But my point was here that p divides this 2m square and 2n square, but they both are relatively prime, like this, not relatively prime, but they have the GCD too. So that is why it would divide the term too. So p will be
Yeah, I
2.
have realized.
Yeah, we'll be seeing the Olympiad problem later in the slides after covering all the theory. So just wait for that. Okay, so let me clear that. So in both odd cases, we won't get the primitive Pythagorean triple. Okay, there's a chat popping up. Yeah, I'll let you know. So just keep the questions related to talk. And let me complete and then you ask questions. So, okay, in both odd case, we won't get primitive Pythagorean triple as A, B, C will be even at the same time, as we want that A, B, C are even at the same time. So does that make sense why we can't find? So what I mean is we have A square plus B square equals C square. So they both need to be even or they both need to be odd at the same time.
Yeah, so C square would also have the same factor in A and B, right?
So then in that case, the GCD won't be 1.
Yes.
Okay, so that should make sense. And let's see the next slide. So we can say that we only get primitive Pythagorean triple if and only if m and n are co-prime, or in other words, we can say that one of them must be odd and the other one must be even. So you can see that from this slide.
So
This
can
one.
we say that C square will be always even?
C square won't be even every time. You can see the example of 3, 4, and 5. If it's even, so that won't give us a primitive Pythagorean triple. That is 6, 8, 10. You can see from that.
Okay.
And let me clear this. So is this the only way we can find all primitive Pythagorean triples? Like this way, using this thing, parametrization, and then we find n square minus m square, and then we try to find the contradiction. And so our claim, so is this the only way we can find all primitive Pythagorean triples? So we'll see that we can say that for any sum, for some integer k, we have this equation, and actually it's not primitive Pythagorean triple here in this case, because its GCD would be k. You see why? Because a square plus b square equals c square, and you substitute k, you multiply k to them, so its GCD would be k, as we have an integer k. Does that make sense?
Yeah.
Yeah, feel free to unmute and speak.
You just multiplied k now. Like there is
Yeah.
nothing new here now.
No. We multiplied k to all the three. Like we used this equation, that's ka equals n square equals to n square minus m square, kb equals to mn, and kc equals n square m square. So what my point was here, that we cannot always guarantee that it will always be k equals to 1. So the
Oh,
probability thing is that m and n, that we need to find, we need to solve for m and n to have that primitive Pythagorean triple. For instance, you can take 4, 3, 5 and then try to make equations with this. So you'll need to find, it will be a very problematic thing to find all n square, all the values of n and m with this. So you'll have 3k equals n square minus m square, 4k equals 2mn, 5k equals n square plus m square. And now you try to find all the values of m and n. So it will be a time taking thing, and you need to maximize your accuracy and efficiency. Yeah, but my point is that it will take a lot of time for other triplets. Okay, so let's move to the next slide. So our claim is that if A, B, and C is a primitive Pythagorean triple, then exactly one of them would be even. So we saw that in the previous slides, that not all of them can be even, not all of them can be odd at the same time, like A, B. We are talking about A and B. We are not concerned about C at the moment, as we saw that GCD of AB, if the GCD of ABC is equals to 1, so that means that if this is equals to 1, so that means that GCD of A and B would also be 1.
yes.
So using that thing, we are not interested about C at the moment. So we'll actually have to find about A and B. So exactly one of the A and B has to be even. Okay, so let's move to the next slide.
Yes.
So we have this equation that was a square plus b square equals c square. So we let b equals to 2k. Does anyone see why we let b as 2k from this thing?
Yes, because anyone can be even on.
Yeah,
To
right.
make it even.
Yeah. So anyone can be even, or any so one of them has to be even. So we suppose that b is equals to 2k. So we can find this thing. Then so we use the formula of a square minus b square, and we find this. You send the 4 here to the denominator, and you find the value of k square, that is c minus a by 2 times c plus a by 2. Does that make sense, or anyone has any questions?
No, clear.
Okay. So as you know that a and c are relatively prime, Similarly, we can prove that c minus a and c plus a by 2 would also be relatively prime. So you have that property where if a and b are co-prime, so their sum and difference of both the terms would also be co-prime from the
Yes.
arithmetic modulo thing, that is a congruence to c modulo m and b congruence c modulo m. So there you can do from that. Okay, let's move to the next slide, and that is as the product is a perfect square. So you see from here that k square is equals to c minus a times c plus a by 2. So their product is actually a perfect square, that is k square. So they both must be perfect squares as well. Like they both could be individually or one of them could be one. But we'll see that they both must need to be perfect square, both of them. So set m equals to root c minus a by 2 and n equals to root c plus a by 2. So what do we have for the value of b? Anyone see how we can find b?
Yes, yes. We have the value of k square is equals to the c minus a by 2 times c plus a by 2. So from there
Yeah.
we can find m and n.
Yeah, you can find the value of b equals to 2 by n from b equals to 2d, like b equals to this thing, you set that and you find the value of this. So m and n are relatively prime, and you could use that fact, like m and n would be relatively prime because their sum and the difference are also relatively prime. So does that make sense, or anyone has any questions? We'll begin the problems in a few minutes. I just wanted to cover the theory for the problem so that we can get started. Okay, so I'll take that as a no and proceed to the next slide. So now let's see what we have from everything that we did. So we'll make a theorem out of that. Not make, but that's actually made before, and we're just trying to study that. So this is the actual Pythagorean theorem. So you can read about it and you can read that. So it says that you have x, y, z be the primitive Pythagorean triple where y is even. You could take x as even as well, but just a clever thing. Then there exists relatively prime integers s and t so that we can make this equation, like this three variables in terms of s and t and s and t. So this is actually a parametrization that we saw before. So we can also make a converse thing of it. So we can say that if s and t are two integers with the condition that one of them is even and s is greater than t, so you could take t as t greater. So why can't we take t greater than s in this case? Does anyone see that?
Yeah, x would be negative.
Yeah, and lengths can't be negative. Actually, it can be, but not in Euclidean geometry.
When can be it negative?
It can't be negative in Euclidean
Like
geometry.
from number three point of view, then it can be negative. But if we are talking about Euclidean geometry, then it's not.
Yeah, I'm talking about Euclidean geometry. So we are actually trying to find the solution for like all the literal rational solutions of it.
Oh, okay.
And we need to, we are working for the positive solutions and not the
At first,
negative ones.
this title of the stream seems like Pythagoras theorem and its application. So it seems like you will be going through application geometry problems, but here is completely different because you are much into number theoretical aspects.
Yeah, I said that before, like the starting of the session, that will be covering a few geometrical point of from the geometrical point of view, and later we'll be starting with the number theory point of view. So it's basically most of number theory point.
Yeah. Okay.
So let's does this theorem make sense to everyone?
Yeah.
Okay,
Yes.
so let's move to the Fermat's last theorem. It's one of the most famous applications of Pythagorean theorem. So what Fermat did, okay, so what Fermat did was he supposed that n is a positive integer greater than 2, then there are no positive integers x, y, z to like there are no positive integer solutions of x, y, z such that this equation, for this equation, that is x to the power n plus y to the power n equals z to the power n. So we'll be seeing this. So this is a Fermat's last theorem definition and nothing special. Like it's a very special thing, but yeah. So continuation of that. Fermat had himself given a proof for the case n equals to 4. So he gave the proof for n equals to 4 and also for the proof for multiples of 4. Like you find x to the power of 4k plus y to the power of 4k equals z to the power of 4k. So this does not have a positive integer solution. So it could be thought of as x to the power, let me annotate. So this could be thought as of x to the power k, and there are raised to the power of 4. So they can be thought as of individual powers.
This session will be uploaded on YouTube because I am running out of mobile data, so I have to leave, I think.
Yeah, it will be uploaded on YouTube and I'll also post the slides.
Okay, thanks.
No problem. Okay, so let's move to the next slide. If anyone has any doubt, they can unmute and speak.
Sorry, I did not know why it cannot have positive integer solutions.
Yeah, we'll see it in the next slides. So it was Andrew Willis who came up with this proof, but he involved a lot of advanced mathematics to prove that. That was modern number theory and algebraic geometry. So you could read about that if you have some knowledge about modern number theory and algebraic geometry, but it involves a lot of higher stuff. Okay, so let's move to the next slide. That's now we see the method of descent. Like we'll be focusing on infinite descent. So this was the theorem we saw, but like what Fermat did was he gave a proof for something stronger than that. That was for x to the power 4 plus y to the power 4 equals z squared. This could be actually thought of in this equation, that is x to the power of 4 plus of y to the power of 4 equals to z to the power of 4. So you can make, like, you can take this as a to the power of 4 and let it as a square raised to the power of 2, and then say that z is equal to a square. Does that make sense?
Yes, you just substituted z for a square, right?
Yeah, right. So, okay, there's a chat. Okay, so everyone has understood. So what is actually method of descent? It is a clever way of using method of induction and contradiction. Like you suppose something and then you try to induct on it and then you find the contradiction. So we'll see how that works. So we begin by supposing that this solution, we begin that the solution to this equation is xyz and it is minimal. By minimal, I mean that they are primitive or the least value that we can find. Like if we have an homogeneous equation, so we can have, if we have the solution to it as xyz, so we can say that it will have a family of solutions kx, ky, kz. So no, don't worry about that. We'll discuss it later. So any doubts as of now? Okay, I'll take that as a no, and let's move to the next slide. So what we can do is make this equation as, so let me write that, x naught square plus y naught square equals to z square. So this is actually a Pythagorean theorem equation. So we can have a so if we have both x naught square and y naught square as 1 mod 4, we'll get z square congruence to 2 mod 4, which is actually not possible because for squares you have 0 and 1 mod 4. So I think everyone knows about that.
Yeah.
Okay, so then we can't have both of them odd at the
Can you
same
explain
time.
just a little about this? I don't know it.
So you can take n as 0, 1, 3, 1, 2, 3. So that will be mod 4. So these are the solutions for n if we take mod 4. And when you square these, you can square and check. So you will have n square congruence to 0, comma 1 mod 4. So this is the thing. You can square 4 of them and check by mod 4. Does that make sense?
Yes.
Okay. So both of them can't be odd at the same time. If even if you have z square congruence to 3 mod 4, like x square congruence, actually squares are always congruence to 0 and 1. So let's see the next slide. So if we have, so this was the thing we saw. So if
I
both of
didn't
them
get
are,
why.
go ahead. Yeah, you can speak.
Sorry, the last point I don't understand. What's the purpose of writing this?
This thing,
The last point, this whole point.
this thing, right?
Yes, yes.
So they both can't be odd at the same time because for odds you have 1 comma 3 mod 4 for n.
Okay.
So if we have a odd number, we'll get n congruence to 1 comma 3 mod 4. And when you square that, you'll always have n square congruence to 1 mod 4. So that is why we included both these case of odd numbers and they don't satisfy.
Okay.
Okay, so now we have that both of them can only be even. So we substitute them to be 2a and 2b, and z will be a multiple of 4 because you see why it's a multiple of 4. You can unmute and speak.
Yes, because z is x square plus y square. So 4 would.
I mean, you could see it from here. That was n square congruence to 0 comma 4 0 mod 4. So it has to be a multiple of 4.
Yes.
So that is why z has to be a multiple of 4, and we included z equals to 4c. So now we again need to find this thing. But wait a second. Isn't it the same as this thing? Like the x to the power 4 plus y to the power 4 equals z square. This is the same as a to the power of 4 plus b to the power of 4 equals to c square. So this means that a, b, c is the solution to our original equation. But this is lesser than the value that we actually used to find it. So that was this thing. Let me move to the previous slides. So we suppose that x, y, z is minimal, and we found that a, b, c is the solution to our equation. So this gives you a contradiction. So anyone has an aha moment from this, or someone too excited about this thing?
Yeah, it looks cool.
Yeah, definitely. It's one of the most famous things that Fermat has given. So now let us take x naught and y naught to be even and the other to be odd. That was from this thing. Where did it go? Okay, I have to move. Okay, I'll explain it here. So we are taking this as the primitive for the primitive Pythagorean triples. Like we need to find the parameterization by taking x naught and y naught to be even and the other to be odd. So we'll see from this thing. So we take this thing n square minus m square and y naught equals to mn and z equals to n square plus m square. But we already suppose that x naught is equals to x square. We are actually found it here. Let me move to the slide.
Yes, yes.
Um, So, so yeah, from here. So we found we are using this substitution right now. So let me move to that slide. So we are substituting x naught equals to x square again, and we find that x square is equals to n square minus m square. But you can move this m square to be to the left side. Like you can move this to the left side, and it will become m square plus x square equals to n square. So x comma m comma n would be a primitive would be a Pythagorean triple. We actually don't know if it's primitive or not. And so we can rewrite this as x equals to t square minus s square. Like we are rewriting the parameterization for this primitive, like this Pythagorean triple, that is x comma n comma n. So we found the value of x and n in terms of t and s. So does this make sense?
Yes.
Okay, now we are very close to seeing one of the most famous results. Okay, so now we do the similar thing for y naught as well. So we can take y naught, y square equals to y naught, which is equals to 2mn equals to 4st times s square plus t square. But we found that 4st and s square plus t square have to be relatively prime so that this they could match up with this y square. This should be q here. So that they can match up with the left hand side that was y square. So does that make sense, or anyone has any doubts? Okay, I'll move to the next slide, and that is this thing. So we can take 4st equals to y square and t square plus s square equals to v square. Okay, there's a question. Yeah, I'll give a 5 minutes break and we'll start the problems. We are very close to completing the theory. That is, we are on the 29th page and we have 3 more pages to go. So just bear with that. Okay, so we can take 4st equals to y square and t square plus s square equals to v square. We saw it from here that both of them need to be individually perfect square. So if we take 4st equals y square and we find st equals to y by so we send the 4 in the denominator and we find st equals to y by t whole square. As they are relatively prime, both of them will need to be individually perfect square, that is s and t. So we found that s and t are both relatively prime, so they both need to be individually perfect squares. So we can take s equals to k square and t equals to a square. Don't worry if you see many variables here. It might confuse you, but if you do it 1 to 2 times, you will be able to understand this. So we can plug this in this equation. So we find L to the power of 4 plus K to the power of 4 equals to V square, which is another solution to the equation Kx to the power 4 plus Y to the power 4 equals to Z square. And we found another solution, which is also not minimal. So now only one thing is left now, that is we show that V is less than C, that is V is minimal solution and not XYZ. So we can say that V will be always lesser than V square as we are talking about the positive reals, and it is V square is equals to T square plus S square, and this T square plus S square is equals to N. So we can we found this from here. Let me show you that. So N is equals to T square plus S square. We use that fact from here and then we substituted it here. So N square plus M square. So N will be always less than N square plus M square, which is equals to Z. This gives us a contradiction as desired. So our actual claim was that X, Y, Z are the minimal solutions, but we found a minimal solution, that is L to the power of 4 plus K to the power of 4 equals to V square, that is LKV. So this completes our proof. So I'll give you a 5 minutes break and we'll start with two problems. That will do two problems and I'll give you one as homework. Does that seem good?
Yeah.
Okay, I'll show you the problems. So these are the problems. And one IMO problem as well. So if you like, you can start working on it, but I'll be away from the keyboard, so I'll not see the chats and I'll be back in 5 minutes. Okay, so is everyone back?
Yeah.
Okay, so just give me a moment. I'm sharing my screen. Um, Just a moment. So let me make my iPad as co-host. Okay, so okay, so can you all see my screen?
Yes, yes.
I think it's lagging.
Yeah.
Okay, let me fix that. Okay, let me stop the screen sharing. Okay, so maybe we'll have to do it here. I can't use my screen. Okay, I'll explain you this problem. Let me do the screen sharing again. Okay, so these are the three problems. I'll give you this one as a exercise that you can try at home. We'll go over this one as this one is easy, and I'll try to upload the video solution to this one because of some technical reasons I'm not able to do it now. Okay, so did anyone try this one?
Yes, sir.
Okay.
Yes.
Okay, so what did you get?
Sir, there are no solutions.
I got 0,000000.
Yeah. That is their image.
Yeah, so the only solution is 0, 0, and do you want to explain how did you do?
Put it mod 2, then replaced it, then again took mod 2, then again replaced, then again took mod 2 and got to the same equation again.
Yeah,
Yeah,
so yeah, I actually wanted to cover one thing that this is a homogeneous expression, and if you have the solution as x, x prime, y prime, z prime, so you'll have a family of solutions that is kx prime, ky prime, kz prime. But here you'll have to find it using that the solution has GCD1, and then you try to contradict it that as you have everything as a multiple of 2. So does that make sense?
yes.
Okay, I'll try to
Yeah.
upload the solutions to these two problems, and you can do this one. So I'll upload the solution to this one as well. So this is an open problem, that is find a cuboid with all integer sides and integer diagonals. So will not be over.
That's Euclid brick,
Will
right?
not be. Can you repeat that again?
That's the Euclid brick, right?
Yeah, I wrote it here. This is the remark on this problem, and you can like this is an open problem. There might exist some other method to solve this, but the problem calls the reader to use the parameterization techniques, and also known as the Euler brick problem. So thank you everyone for your attention, and thanks for coming as there were very few participants. And so this is the ending slides. Any questions? You can email me or you can ask me on Discord. So here's my email. And Please fill out the feedback form so that I can improve for the next session. So thank you everyone. I'll stop the recording now and also upload it on YouTube.
Have a nice day.
Any questions do you have? Stick around if you want to have, if you have any questions or want to ask anything.